All right, we now consider the Solow model with only capital accumulation. Let us still start with capital K and labor L, which produce an output Y, but as you're going to see, we will get rid of L very quickly. So we can write it in a very simple way. So Y output is equal to a function of my two factors of production, K and L. For now, we can what we want to do is to assume that L is fixed, so that way we can just not have to think about it. So let's just assume that L equals 1, since I can choose any value I want. And also imagine that the rest of the economy is also fixed. So land is fixed, technology is fixed, nothing changes. Why do we start with this? Well, because it's perfectly fine. It's enough to look at most of what's interesting in the Solow model, and then we can add complexity once we understand the basics. So let us write it this way. So Y equals f of k1. And I can even abuse the notation more by just writing it is equal to f of k. So where has the L gone? Well, the L is still there. So maybe I shouldn't write use the exact same letter for f. But so if we allow for this abuse of notation, so we have to simply remember that the L is still there. But since it doesn't change, I don't have to care for it. Now capital has its usual properties in terms of production. So it has decreasing marginal productivity. What does that mean? Well, first of all, if I have some positive amount of capital, I should be able to produce some positive amount of production. So f of k is greater than 0 for k greater than 0. Then what happens if I increase the amount of capital by some positive quantity? Well, I should be able to produce more, or some quantity more. So I write df of k dk is also positive, but there are decreasing returns. So what does that mean? It means if I have, say, a very large amount of capital, then at some point it doesn't give me all that much. If you give me even more capital, I can't exploit it very well. So its impact on output is even more than before. So how do I write it? D square f of k d k square is 0, or the second derivative of f of k with respect to k is smaller than 0. So these are our basic properties for f. So if you want to want some example in mind, so what we can think about, Cobb-Douglas would be fine. So here, since we have only one variable, so let's just say it's f of k is square root of k, for instance. So example, I could write f of k equals square root of k. And then I can verify that my choice indeed works with the assumptions I have. So if you remember how you derive, so df of k dk equals 1 over 2 root k, which is indeed positive for any positive value of capital. We don't consider negative values of capital, of course, because it's only a positive quantity. And then second derivative, so I again derive this expression a second time. So what do I get? I get then, since k is at the bottom, then I'm going to get some negative amount. So minus 1/4 multiplied by 1/k to the 3 halves. Oops, 3 halves. And this is indeed smaller than 0. All right. So this is a basic function that would be valid for that. So keep that in mind if you're confused. So now let me add some extra assumptions. So these assumptions are called INADA conditions. They are necessary if I want the model to be well behaved, and by that I mean to have to be sure to have one equilibrium, and that this equilibrium is unique. So for now it's abstract, you don't really know what I'm talking about, but once we see what happens graphically, everything is going to be very clear. So first assumption is no capital, no production. So in a way, if I had no capital, maybe I could build some things with my my own hands. I have some ability, but here we're going to use this simplifying assumption. So I can write it very simply. F of 0 equals 0. All right. And now the maybe tricky assumption is we're going to say that the first unit of capital is infinitely productive, or is has an arbitrary large marginal productivity. So this again is going to make sense down the road. So how now just take my word for it. So how do I write this? So I'm going to use limits. So the limit when k tends towards 0 of df of k dk equals infinity. All right, so this is my second INADA condition. And then the second one, the third one will be actually the reverse of the second one. So and this one makes a lot of intuitive sense. So if I have an infinite amount of capital, then one extra unit doesn't give me anything in terms of production. So the marginal productivity of capital towards when capital tends to infinity is 0. So I can just rewrite this the same way and replace here. So the limit when k tends towards infinity of df of k dk equals to 0. And we can verify that these assumptions are verified for our choice of function. So if I look at the first derivative, so df of k dk equals 1/2 square root of k. So what happens when k tends towards 0? Then this tends towards infinity. So I can't express this if k equals exactly 0, but towards 0 it makes sense. And if k tends towards infinity, then I get 1/infinity. So I get df of k dk equals 0. So this is valid for the third INADA condition as well. All right. So this is everything I have to know about f for now. Now what I want to know is how do I accumulate or lose capital? So as we have said, we have some ways to gain capital by investment, and we lose capital over time due to depreciation. So this depreciation rate is exogenous. It's going to be delta. Delta is a fraction of capital that I lose every period. So then the total capital loss is what? Is simply delta multiplied by the capital I have. Here I haven't introduced any time period yet, so we don't know what this is, if it's 1 second or 1 year. It's just a fraction of capital. And what can I do to mitigate this loss of capital? Well, I can invest in more capital. And to invest, I need to save some of my output. So here the savings rate is some fraction S, that's between 0 and 1. Agents can save this as fraction of their income and reinvest it. So what is total investment? Total investment is going to be written I equals to the fraction of production saved S multiplied by the total production. And I can already substitute F. So I can write S times F of K. So this is investment. Now, question for you. Think about it for a while. What is consumption? All right, here's the answer. Well, consumption is whatever is left after I have invested. So if I go back to the example of potato plants, then I invest some potatoes by planting them, and the rest I can keep and eat for myself. So I could write consumption I will write it C equals Y, what I produce, minus what I invest, S of Y. And in terms of, I can also write 1 minus S times F of K. All right, so this is nice because we have everything written as function of K, and we're going to be able to not really care too much about these capital letters. All the models will be well expressed in terms of K. So this is the capital accumulation and loss. Now, I haven't said a word about the dynamics, but this is a dynamic model. This is all we care about. So we can introduce time in typically in two ways, either as a discrete way or in a continuous way. Here we start with the discrete way, which makes intuitive sense. However, once you get experts, you see that dealing with continuous time can be simpler in terms of the math, but they are mostly similar. So here let us introduce time. So we're going to say that time is just some value t, which can have value 1, 2, and 3. So I'm not saying whether this is some years, for instance, or months, but yeah, years makes sense. It depends on what data you have, and when you do have to work with data, then you will have to be careful about making sure that your units of time are always the same in each of your data sources. And finally, we can talk about the growth rate of capital. This we call the law of motion. So it's the rate at which capital will change. And then what is it? Well, we already know that there are two ways to change capital: by investment and by losing capital through depreciation. So how do we write this? Well, it's very simple. Again, we're going to express capital in a discrete way. So what we write is the following. So the change in capital from one period to the next can be expressed as k t plus 1 minus kt. Oops. And we're going to use a Greek letter for that. We're going to define this as, oh yeah, I can write, since we define it, capital delta kt. So this is the definition of kt plus 1 minus kt. And it's equal to investment minus depreciation. So S y of t minus delta k. Right? And yeah, I can even replace y of t, so s f of kt. So this is how much capital will change from one period to the next. And so one note is, if I was dealing with continuous time, then instead of having capital delta k t, I would simply consider time derivative, so dkt dt, for a very small amount of change over time. So it's like if I always look at how much capital do I have, and we write this as k dot t. Now, final concept to understand is what we call state variables. So here, k is going to be a state variable. What are these variables? Well, they are a set of variables that contain all the information that we need to describe completely a system. Here, the system is the economy, and to know everything about its future evolution. So here, since there's only actually one variable that really describes some stock, which is capital, then once I know it, I know everything I have to know. So this is the mathematical expression of the model. Now we're going to see it expressed in terms of graph, and everything is going to make sense.